All right, so in this one here, we're talking about domain and range. Now, this is a concept that you would have talked about a little bit in grade 10. Might not have been a big focus, but we're going to make it a little more important this year. So, domain, it's the set of all the values that the independent variable can take in a relation. And so the independent variable, that's the x value, that bottom horizontal line on the graph. Those values there, any value that the x value can take, that's the domain. The range, that's the set of all possible values of the dependent variable that the relation can take. So that's the vertical axis, that's our y-axis in general. These values vary depending on the situation. They could be affected by the real world situation that's involved. If it's someone, launching a rocket, jumping off a cliff, the temperature swings of a climate, all sorts of things that are embedded in the real world, like is the Earth ever, if we were talking about temperatures on Earth, will we ever hit negative 273 degrees Celsius? Probably not. So, we're kind of have a range there that's going to limit our temperature. So these things are kind of limited by the situations in the real world. So that's why we kind of take a look at these, is that we want to know in a given situation with a given equation, as we're modeling things mathematically, where are we limited with our model? We can have an equation mathematically. In the equation, things can go forever. If we're modeling launching a rocket, it's going to go up, it's going to come down, it's going to hit the ground, but mathematically in the equation, it can go into the ground. Probably not going to happen. So we have a domain and a range to limit some of those aspects of it. Now, when we're talking about domain and range, it's important to know some of our number sets. Hopefully you're familiar with a lot of them, but as a review, the integers and real numbers of the two we're probably going to work with the most. Integers are all possible whole numbers, positive and negative, including zeros. Whole numbers, what are they? Well, let's start with the natural numbers. Natural numbers, naturally, if I said, hey, start counting to 100, you're going to start at 1, 2, 3. The natural numbers are naturally what you would start saying, which is 1, 2, 3, so on and so forth. The whole numbers just tack on a 0. Naturally, we don't think of adding 0 as a number, so the whole numbers include 0. And when we want to talk about integers, well, we need negative numbers. That's all we're doing, is just slapping in the negative numbers. So negative 15, negative 75, positive 623, 498, those are all integers. There's no decimals, and when we want to denote them in our mathematical sentences, we either use a bold capital I, which you can draw out just a really big bold I. I was brought up with a notation where you just kind of use this double bar in the middle to denote that it's bold, and you'll see both of these and depending on the textbook that you're using. The other set of numbers we want to use, and there's a whole bunch of them out there, but we're going to look at just the integers, which you should be pretty familiar with, and then the real numbers. And the real numbers just mean all the integers, including the decimals or fractions. So any decimal, any fraction that you can name, that is included in the real numbers. There are number sets that are complex or imaginary number sets. We're not going to deal with those. We're just dealing with the real numbers. So if you can, pretty much any number you can name me, unless one of you throws out, I, the square root of -1 kind of thing. If you can name the number, it's a real number. All the integers fit in the real numbers, but all the real numbers include the values in between the integers as well. We use capital bold R, or again, I use the double bar. That was what I was brought up with it. So working with domain and range, when we want to list it, we have a couple notations for it. So we'll look at those as we look at some domains and ranges of a couple situations here. So I did steal these from the textbook, so you can take a look in the textbook too and see those as well. But here we have the domain and range of a couple graphs. So this first graph here, if you note, and my apologies, everything didn't line up on the grid lines. Would have been nice. Probably could have drawn them out, but that would have taken way too long, and my printer needed some use. Each of these points is at an integer value. This would be 3, 4, and 5, and then 4, 3, 2, and 1. Everything lines up nicey nice. So we can look at our domain and range. They're all integer values. There's no values in between the points. Okay, there's nothing in between here. So because there's no values that we're noting in between the points, we're just going to use an integer value for our domain and our range. So the domain, there's two ways of doing this. One is set notation, and so we can note the set, and we use curly brackets to note the set of values, and we can just list out all the points, and so that's going to be the set of 2 and 1, comma, actually, sorry, I'm listing the points. We just want to list the x values. So we can list the x values. So 2, 3, 4, and 5. Those are our x values. And then the range using set notation would be 1, 2, 3, and 4. So the set of 1, 2, 3, and 4. So there's our sets. This can get bulky if we have like a whole bunch of numbers. It's okay for generally for integers if we have a small set of integers. But say you had like 100 points, this is going to get pretty awkward to write out. So we could use, especially if we get bigger sets, the notation, the set of. So we always still use the set notation. And again, my curly brackets are generally terrible. Don't worry about drawing them perfect. As long as you kind of note you got a bracket with a ball at the end, it's all good. You can also use the pointy notation. So in this case, we have the set of integers. So we have x, so the domain is x, belonging to that e, okay, e, it's kind of like a C with a line through it, it's like a Greek E, stands for belongs to, the integers, the big bar, such that okay, so x belongs to the integers, so it just tells us x is a bunch of integer numbers, belongs to the integers such that 2 is less than or equal to x is less than or equal to, what's our big one there, 5. Now, this notation here, probably a little longer to write it this way in this case, but depending on how many you have, it could be a lot easier. We'll see that in a couple of the later examples. Same thing with the range. The range is the set of y, and again, it's a set of integers, so belonging to the integers, such that, and in this case, y is between 1 and 4. 1 is less than or equal to y is less than or equal to 4. So there's our integer set. Now let's take a look at the second one. We have our points here at 1 and 2, and then and this is noting just so on and so forth. It's continuing on 1, 2, 3, 4, 5, 6, so on. So there's a whole bunch of points here. So if we try and use set notation, we got 1, 2, 3, 4, to infinity. And that kind of looks, I don't know, it looks awkward, it looks ugly, to infinity. Do we know it's going to infinity? What's infinity? Infinity is like a weird concept anyways in math, but that's kind of what we put there. The dot, dot, dot. We could also just put, to n for some unknown number. But again, it's kind of awkward. So if we write it in this notation, we can just say x belongs to the integers such that x is... Oh, and I actually missed one there. Sorry, there was actually a -1 and 0. Let's tag those in. -1, 0, comma 1. Sneak those in. Such that x is greater than or equal to -1. That tells us that as long as x is bigger than 1 and an integer, we're all good. This is a better notation in terms of set. Small number of values, this set notation is okay, where you just list the points, but this set notation here, where we have the set that it belongs to and then the restrictions, that's probably a better variation when we have a large group of values. Let's take a look at the y values here. Y is really easy. Y is 2. The range is 2. Y value is always going to be 2. That's it. That's all. So that's a nice, easy way to say it. And again, if we use the larger notation, y belongs to the integers such that y equals 2. Kind of boring. Probably good enough just to use the first version. So different variations depending on what just makes more sense in terms of the situation. Now, in the next 3, this is where we want to take a look at the second version because it's kind of hard to list all the points. What are all the points in here? Well, there's 0 for the x value, and there's -0.00000000. I'm tired of saying zeros. 1, 0.0000000002, 0.00000003, and so on and so forth. It's going to be too many to write. So that's where we just use this nicer notation here. We just say skip the first type, and we'll write it out. X belongs to the real numbers, because they're decimals, such that... actually, there's no restrictions here. X can be any number. We're done. So we only put the such that if there's a restriction. In this case, there's no restrictions. X is anything, right? This line's going to go forever and forever. Either way, X is good. Actually, sorry, no. In this case, there is a restriction. There's no little arrows. It's hard to see on this page. I'm getting old. I probably need glasses or something. We're actually limiting it at 4. The arrows, notice the other ones have arrows that kind of keep it going. And that's -2 kind of here. So x belongs to real numbers between -2 and 4. So -2 is less than or equal to x is less than or equal to 4. And that's kind of our between notation. It's you put the x in the middle and then it's between the two numbers. Just both of them are less than or equal to. The range, same idea. Max at 2, minimum of -2. So the range, y belongs to the real numbers such that -2 is less than or equal to y is less than or equal to, or no, it's a 3. So -3 is less than or equal to y is less than or equal to 2. I'll erase that, clean that up. Someone's going to complain if they can't read my writing, and they're not going to listen to me as I ramble on. There's our notation. Okay, a couple more. Next one here. So we have a limit on the x starting at 0, and then it continues on, and that arrow tells us it's going on forever. So x belonging to the real numbers in this case, such that x is greater than or equal to 0. That's it. It's bigger or than 0. The y values, y belongs to the real numbers again. Same idea. such that, and y starts at 2 and then just keeps going down lower. So y is less than or equal to 2. That's it. That's all. And then our last one, we got this parabolic function. It's going both left and right, positive and negative, forever on the x-axis. So x belongs to the real numbers. Done. There's no restrictions. It keeps going forever, so it's just any real number. Now, the y does have a restriction. It has to be greater than 0. So the y belongs to the real numbers such that y is greater than or equal to 0. That's it. That's all. And that is our different notations. So now let's take a look at an example here. Working with a couple different scenarios. What's the domain and range if you're given just a set of points? Well, the domain is all the x values. So the domain, and in this case, it's probably just easy to write the actual points, is -1, -2, -3, -4. And we might write that, that was a terrible bracket. Might write that in the opposite order and write -4, -3, -2, -1. Put them in actual order, but that works. It lists them all. Order is not required in a set. Just sometimes it's convenient. And then the y values are all the corresponding y values. 1, 3, 5, 7. 1, 3, 5, and 7. So the set of 1, 3, 5, 7 is the range. That's it. Domain and range in the case of this, so again, we got a parabola, similar to the example on the previous page. The arrows mean it continues forever this way and this way, so it's going to go on and on and on, and because it's going on and on, it's going to hit every x value. The domain is the set of x belonging to the real numbers, and that's it, no restrictions. And then the range is going to be the y value belonging to the real numbers. But there's a restriction. It's got to be greater than, and this is counting by 2, so this is -2. So y has to be greater than or equal to -2. And you got to include that equal to. There are situations where it wouldn't actually hit the -2 for whatever reason, and so then it would just be greater than -2. And then if y equals 6, well, no matter what the x value is, there's no restriction on the x value. And if we were to graph this, put it on a graph at -6 here on the y-axis, you just have a line going straight across. That would be the graph. Pick any x value you want. Y is going to be -6. And so you have a domain of x belonging to the real numbers. There's nothing preventing x from being whatever it wants to be. But no matter what x is, the range is simply just 6. Or, sorry, -6. I did that whole backwards. Sorry. That should be like down here at -6. That's way wrong. Thanks for catching me. Yeah, so that whole top part, bad. -6 down there. Y is equal to -6. That's our range. And then, like I said earlier, some of these are restricted by real world situations. So if we got Billy here, and he's taking a jump off his 10-foot shed. So he's got the shed, it's 10 feet up in the air. He's jumping off there, he's jumping up 2 feet, and then he's going to hit the, he's going to dive into his pool, because don't do this. This is probably a bad idea, but it was what I came up with. I may have been watching kids out my window jumping into their pool off their shed roof. So he jumps off his shed roof. It's 10 feet up in the air. Jumps 2 feet up into the air, and then lands on the surface of his pool after 1.4 seconds after jumping. So if we were to quickly diagram this, This is going to be his height. This is going to be the time it takes. At 0 seconds, he's at 10 meters high, or 10 feet high. He jumps up a couple feet and then plops down. So this is up at 12. This is just a quick little sketch. Nothing to it in terms of being exact. This is 1.4 seconds when he actually plops down in the pool. Does maybe a belly flop. So our domain and range are now restricted because we're worried about him just hitting the surface of the pool. We're not worried about being under the pool. We're not worried about anything with negative time because that would require the ability to do some time travel, and we're not doing that. So if anybody figures that out, by the way, you get 100% in the course if you can travel through time and prove it. So we got travel backwards through time, let's say that, because we are traveling forwards through time. So let's do our domain. Domain is 0 to 1.4 seconds. It's a real number because it's all the values between there. So x belongs to the real numbers such that 0 is less than or equal to x is less than or equal to 1.4. And our range, well, that again is limited. Again, real number. This is going to hit every distance between 10 and up to 12 and then back down to 0. So y belongs to the real numbers such that 0 is less than or equal to y is less than or equal to 12. And that puts it in between. And there you have domain and range.